Here we have a man drowning in the sea, Mike, and here is Lassie, who's going to save him. We need to figure out the best route for Lassie to take from the beach in order to save him. We will do so by optimizing a function of time. Here is some necessary information. Point B is Mike. Point C is the point on the beach orthogonal to Mike, in relation to the beach, and point D is the optimal entry point for Lassie, assuming Lassie is faster on land than in water. X is the distance from Mike to the beach, Z is the distance from Lassie to point C, and Y is the distance from the optimal entry point to point C. We will represent Lassie's speed on land with r, and her speed in water with s. We now need to set up our function of time. Our equation is going to be time, t of y, equals the quantity z minus y, which is the distance Lassie will travel to the optimal point of entry, divided by r. Then add the square root of x squared plus y squared divided by s. We use the Pythagorean theorem to find the hypotenuse, which is the distance from the optimal point to Mike. In order to optimize Lassie's travel time, we must find the derivative. We know that z over r will be a constant, and so will be 0 when derived. Negative y over r will derive to negative 1 over r. To make this much easier, we separate z minus y over r into z over r minus y over r. Then we derive with relation to y. So, t prime of y equals negative 1 over r, and we move the 1 over s to the side because it's constant. So, it is 1 over s times the quantity x squared plus y squared to the 1/2. We now need the product rule. We bring down the 1/2 and subtract 1 from the power, then multiply that phrase by the derivative of x squared plus y squared, which is 0 plus 2y, because x is also a constant for us. We've finished our derivative and now we must reorganize. The 2 of the 2y cancels the 1/2, and our final derivative looks like this. T prime of y equals negative 1 over r plus y divided by s times the square root of x squared plus y squared. Now we must find the value of y which minimizes time, t of y, by setting the derivative equal to 0. So, 0 equals negative 1 over r plus y over s times the square root of x squared plus y squared. Add 1 over r to both sides and multiply both sides by s. You square it all to get rid of the square root sign, and we get s squared over r squared equals y squared over the quantity x squared plus y squared. Next, we multiply both sides by the quantity x squared plus y squared. Distribute the s squared and then multiply both sides by r squared to get s squared x squared plus s squared y squared equals y squared r squared. Then get the y's together by subtracting s squared y squared. We then factor y squared out and divide both sides by the resulting quantity r squared minus s squared. Reorient, and we get y squared equals s squared x squared over the quantity r squared minus s squared. So close. All that's left to do is to square root everything, and then we get y equals s times x divided by the square root of r squared minus s squared, the solution which minimizes t prime of y. Therefore, with this optimization solution, r must be greater than s, and neither equal to nor less than s. If r is less than s, we get the square root of a negative number, which is not real, and if r is equal to s, we get s of x divided by 0, which is undefined. Now that we have our solution, we are given running and swimming times by Timothy Pennings and his dog Elvis. We average the speeds we've calculated to find that r is equal to 6.354 meters per second and s is equal to 0.874 meters per second. We can apply these values to our optimized equation, substitute, and get y equals negative 0.874x divided by the square root of 6.354 squared plus 0.874 squared. We do some quick calculating and find that with the given speeds, y equals 0.139x, which will give us Lassie's optimal route if we are given the distances. Pennington spent some time gathering the data shown here. By using Desmos, we can plot the data and use y is approximately equal to 0.139x as the line of best fit. The reason we use approximately is that in Desmos, in order for the calculator to work, we must use the approximately sign instead of the equals sign. We find that Elvis, at least, could be better at calculus. With an r-squared value of 0.3957, there is only a weak correlation between the route Elvis takes and the optimal route that Lassie would take if she were a great mathematician. Now, of course, Elvis is but one dog, and so we are limited on data. And by Pennington's own admission, he omitted some data points where Elvis jumped straight into the sea. This project also assumes there are no other environmental factors aside from the methods of travel, excluding wind, current, and other such factors. Breed of dog could also greatly affect a dog's ability to perform this calculus. Finally, Pennington conducted his experiment with only Elvis as his partner and limited supplies, using only a screwdriver, a tape measure, and a tennis ball. With help, a much better experiment could be carried out to more accurately estimate a dog's math abilities. That's us finished, and thanks for watching.